the difference between charged particles and photons is that charged particles deposit most of their energy at the end of the range. Basically, most of the treatments in radiotherapy use X-rays, which is like light. Light is attenuated in depth. So you have a high dose on the skin and then gradually decreases in the body. Using protons or carbon ions, you have a low dose in the skin, and then when they reach the tumor, they release most of their energy. So that's a big advantage in terms of conformality and in terms of sparing normal tissue, because then you can irradiate only from a few angles and spare a lot of normal tissue. The talk was about the radiobiology of particles. So the point is that there is this physical difference between photons and charged particles, which is very important. But there is also a biological difference. So at the end, when these particles release most of the energy in the tumor, then you have a different biological effect. And this helps in killing radioresistant tumors or very hypoxic tumors. So we have shown today that there is a lot of research ongoing on use of different ions, for example, using not only protons and carbon, but also helium or oxygen, depending on the kind of tumor that you can use. Well, the idea is exactly this one. The idea is that when you make this kind of damage with particles, being hypoxic doesn't help. So let's say at the moment that the tumors live in hypoxia, and when you are in hypoxia, you don't create these free radicals that are very important for X-rays. When you go with ions, it's like smashing directly the DNA. So you don't need oxygen around, you just smash your tumor, and you don't care about hypoxia. It's a little bit like, if I can say, a little bit like I generally explain it this way. I have a daughter. And when I go into a candy shop with my daughter, at the beginning, she doesn't make a lot of damage. I mean, I kind of run quickly, and she tries to take something, but I'm very fast. But gradually, she starts to take candies and candies and candies. And then at the end, she's slow. And when she's low, she can easily grab things. Imagine now electrons. I'm ionizing electrons. Same thing with my daughter and the candies. And then at the end, she's full of candy. My money is over, and she stops. That's the bragg peak. It's what we call the bragg peak at the end. Let's say that this bragg peak, of course, at the end, when you are slow, so you can grab all the electrons around, you are very effective, and the damage that you create is almost impossible to repair. This is exactly because they have this advantage of giving then a low dose in the entrance. Now imagine my daughter again. The entrance of the shop is the normal tissue. And then you are very fast because these carbon ions are accelerated at very high energy. So they enter in the body. At the beginning, they release a little energy. It's like my daughter running. She has no time to grab. But so the damage to normal tissue is low. But when you are in the tumor, now you have slowed down, and now you look around and you create a lot of damage. So the damage to normal tissue will be small, and the damage to the tumor will be high. If you use light, light, if you put something in front of the light, you immediately attenuate the light. So the dose to the skin will be higher than the dose to the tumor. This is a fascinating field. In a way, it's old. I mean, it is known that radiation causes vascular damage, let's say. This is very well known since, the 1930 or so. But these days is coming back, because the idea is that when you go to hypofractionation means very high dose in very few fractions, then it looks like you can damage not really the single cells, but the stroma, the microenvironment of the tumor. So you basically imagine that you can destroy all the vasculature that goes into the tumor. The tumor will die anyway by starvation. So you don't need to kill every single cell. This is very interesting, very controversial, because this seems to work in a way, but on the other hand, looks like the tumors are smart enough that they can recreate new vessels, and then they are back in shape after some time. But it's a wonderful research topic, I think, and there's a lot of research going on in this field.